Welcome, everybody. My name is Chris True, and I led the group of graders that graded your practice exam. And I'd like to go through and talk about not just the answers to the test, but concentrate mostly on what are the things that you really need to do in order to maximize the number of points that you can earn on the exam. All right, so I'm going to go through each of the 6 questions with you and talk about what the answers are, but focusing mostly on what are the things that we're going to be looking for as we actually do the grading during the summer. All right, so this first question, and I'm not going to read the entire question. You guys took the exam and remember what the questions were about. This one was about using a spreadsheet to complete a task. And there was 2 groups. One group was experienced using the spreadsheet and another group was not. And so the question said, of the 2 histograms, 1 or 2, which is more likely to be the distribution of completion times for the students in group R? And group R was the group that was inexperienced. All right, and so the first thing is you needed to be able to answer the question. And the answer was histogram 2 is the one that goes with group R. Okay, and some of you stopped right there, and there's almost always going to be something like justify your answer. Now, the justification is I picked this one because the people that are inexperienced generally are going to take longer, right? And when you answer this question, we've got to assume that the person that is grading the exam is looking for an explanation to somebody that doesn't know much about stats. Okay, so what is it about this distribution that makes this the inexperienced group? It's, well, they take longer to finish the exam or finish the task. And you really needed to say that there was, most of the times were out here at an hour and a half or more. All right, and so in order to answer this question completely, you need to pick histogram 2 and say that those times tended to be longer. And we also need to say, we see that many of the completion times in histogram 2 are between 95 and 115, and that's a relatively long completion time. All right, so the majority of the people were out here at an hour and a half or more to finish this task. Okay, a lot of people did not put that. You didn't identify the location of the peak. Okay, whereas on this one, the peak is at the lower times. Okay, and then the second part of this one says that what would happen if you combine the 2 groups together? So if you took these 2 groups and put them together, you're going to end up with a lot of people are going to be 35 to 55. A lot of people are going to be 95 to 115, and there probably won't be so many in the middle. Okay, so if you imagine what this distribution would look like, it's going to look bimodal, right? And a lot of you did say something about it being bimodal. So if the 2 groups are combined, it would be bimodal. Some of you use the word binomial in here, okay? And I understand that those 2 words are very, very similar, but they do mean 2 completely different things. Bimodal means that it has 2 peaks, right? And a lot of you did say bimodal, but then you also need to say where are the peaks going to be. So there's going to be one peak at around 45 and another one around 105. Okay, that's where the majority of the people are going to fall. All right, you could have also drawn a picture of this and made it bimodal and showed along the horizontal axis that the peaks were centered at around 45 and 105. Okay, a lot of you missed this last part about the location of the peaks. So one thing that I've told my students in the past is that when you're asked to describe something, okay, imagine that you describe it and you've got the picture in front of you, but if you cover up the picture, do the words describe what's under your hand? Okay, and in order for me to do that, I would need to know that this distribution is bimodal, and then I'd want to know where are the modes at, okay, and where is the gap in between them. Okay, and then for the part C, it says consider the population of all students in the biology class. So they're combining the 2 together, and they're going to get this bimodal distribution, and then they're going to take samples of size 50 from that population, and then look at the sampling distribution of the mean. right? So there's a thing called the central limit theorem that says that the sampling distribution of the mean is centered at the population mean. So the mean is 70, so the mean of the sampling distribution is going to be 70. And the standard deviation is equal to the standard deviation divided by the square root of the sample size. Okay, so we needed to see this. Okay, and then the shape of that distribution is, a lot of you said normal. Some of you said it was still bimodal. Okay, but I'm going to tell you that generally speaking, when you talk about something being normal, you really do need to have this word in front of it. Okay, because there are very, very few things that follow exactly a normal distribution. Okay, a lot of things can be modeled by a normal distribution, but they're not exactly normal. All right, so I would say that it's safe to say that if you say the word normal anywhere, putting the word approximately in front of it is probably a good thing to do. Okay, and then the other thing that we have to justify, or that we have to do, is justify the shape of this. Now, if I had taken small samples from this distribution, I would probably end up with something that looks a little bit more bimodal. Okay, but because our sample size is 50, right, and you need to say a little bit more than the sample size that's 50, you need to say that that is bigger than, I think almost every textbook says big enough is 30 or more. All right, so you need to justify why the shape is approximately normal. Okay, so those were things that we saw people miss on question number 1. Okay, question number 2 was a study that they did where they took a bunch of runners. Some of them were professional runners and some of them are recreational runners. All right, and then they gave them different kinds of shoes. All right, and they decided that they were going to block this experiment by the classification of the runners. All right, and so they took the professional runners, they gave half of them one pair of shoes, and the other half got a different brand of shoes. And then they had them run and they compared their times. So this is basically a blocking by runner classification. All right, and then we want to know, what is the advantage of doing that? All right, so a lot of you said you get more valid results or you get better data, or you said things like that, which, you know, are just, that's just kind of garbage stuff that people said. Okay, we really wanted to say something about blocking is basically, it's comparing professional runners to professional runners and recreational runners to recreational runners. And when we do that, the professional runners are more like themselves. Okay, there's less variability in their running times. Professional runners tend to be faster, and they are all faster, and so there's not as much variability from one runner to the next. Then if we compare those to recreational runners, and we're comparing a professional runner to a recreational runner, that group is going to have a lot more variability in it. All right, and so blocking is going to do two things. It's going to minimize a known source of variation, okay, and that is that professional runners tend to run faster, okay, and there's less variability from a professional runner to a professional runner, okay. And then also what's going to happen is this is going to reduce the variability within the two groups. Okay? Being able to compare like people to like people is something that reduces the variability, and we end up with a different kind of a test there. Okay, so why is it important to randomize the type of shoe the runner will wear instead of letting them pick their own shoe? So if you think about it, I think this is probably more pronounced with the professional runners. They know what shoes they like and they know what shoes work well for them. And so they're probably going to pick that shoe, right? Which in that case, they're going to end up running faster. Okay, if we're forced them to wear one shoe or the other, then we're going to get a better idea about how does the performance of the shoe work. Okay, so randomization reduces the possibility of confounding variables. All right, and that confounding variable would be just the familiarity with the shoe. Okay, and the shoe that you like is a shoe that's comfortable, that you're going to be able to run fast in. Okay, a lot of you did use different terminology here. Okay, some of you said reduces bias. Okay, bias is not really something that is in an experiment. Okay, bias has to do with the way that we sample more than the way that we assign things. Okay, so randomization is going to reduce the possibility of a confounding variable within the group. Okay, self-selecting could introduce a confounding variable, and that confounding variable would be familiarity with the shoe. Okay, an example that I gave my students with confounding variables is we talked, when we did experimental design, we talked about a diet pill. And we talked about how we could design an experiment to test to see if the diet pill is effective. And so we decided to do this a couple different ways. First way we did is we just took a bunch of people that volunteered for the study, men, women, you know, overweight people, people that weren't overweight, people that were athletic, people not athletic, and we randomly assigned them to two groups. Okay, and then at the end we compared the two groups, the placebo group to the diet pill group, right? And then we noticed that, you know, the diet pill group lost a lot more weight on average than the placebo group did, right? But then we also looked at that group and we said, man, you know, in this in the group that got the diet pill, there happened to be a lot of males in that group, right? And a lot of females in the placebo group. And a lot of times with medication, men and women will react differently to the medication, right? And I think especially with diets, men, I think this is not a sexist statement, I think this is a relatively true statement, that men generally can lose weight easier than women can. Okay, and so did that group lose a lot of weight because they were men, or did they lose a lot of weight because they were on the diet pill? Right? We can't really tell by the way we designed the experiment. So in my class, we talked about, well, what could we do to help that out? And my students said, well, we should just compare men to men and women to women. Right? And that's exactly what we did. Then we talked about blocking. So blocking by gender in our case, we were able to compare men to men and women to women, and it reduces the variability between the two groups then. Okay, comparing men to men and women to women. All right, so know your vocabulary words, especially for, there will typically be a question about experimental design or about sampling or something like that, that you should know how to pick up all the easy points. Okay, and then there was a follow-up part to this, part C. Explain how the design of the experiment will address replication. All right, and a lot of you whose papers we graded misinterpreted what we meant by replication. Okay, this doesn't mean that we're going to do this experiment over and over and over and over and over and see if we get the same results every time. Okay, the replication here has everything to do with the sample size. Okay, so we don't want to do this just with one runner. Okay, we want several runners so that we can get an estimate of how much variability we would expect to see in each group. Okay, so replicating doesn't refer to replicating the experiment. It means to have a big enough sample size. Okay, and then having several runners in each group allows us to estimate the variability within the groups. Okay, all right, then question number 3 had to do with a probability question. And this one was about STEM students and then being eligible for a scholarship or an internship. Okay, and it says, suppose that one woman is selected at random from the women in the STEM majors at the university. What is the probability the woman selected will not meet the age requirement? Okay, and the age requirement is they have to be at least 20. So these people, and these people don't meet the requirement. So what we saw a lot of you do is just give this for an answer, right? And to be honest, we can tell what you did without seeing the work. However, this is a thing that you should be learning from this experience, that in order to get all the points, you really do need to show the work that leads you up to that answer. Okay, and even though this is a very trivial thing, we do want to see this work. Okay, so if you only give the answer, it has to be right, first of all. You can get a partial. Okay, what's really nice about this also is if you add these three numbers together and you come up with a number that's not this one, okay, but you wrote down these three things, okay, you're going to get full credit. Okay, even if you added wrong, suppose you didn't use your calculator and you came up with, I don't know, like 23.2 or something like that, you can still get full credit by having just the work there. Okay, then we switch over to part B on this one where they say the university will select a sample of 100 women in the STEM majors, and we want to know what's the probability that we're going to get at least 30% of them do not meet the age requirement. Okay, so what we saw was a lot of you got the right answer, right? But again, the supporting work is just as important, if not more important, than the answer. So a lot of you did not identify that the distribution is binomial, right? And there's several ways that you can do that for us when you're writing out your work. You could write what I did here in pencil. X follows a binomial distribution when n is 100 and p is 0.223. Okay? You can also do that this way. Okay? This is standard statistical notation. This says X follows a binomial distribution with n equals 100 and p is 22.3%. Okay, that's perfectly fine. A third way that you could do this is you could write out the formula. Okay, so this is the probability that X is 30. This is the probability that X is 31. Now we certainly would not expect that you're going to write out 70 of these things. So it is okay for you to put plus dot dot dot. Okay, and we know that nobody is probably going to get an answer for this one by using the binomial distribution over and over and over and over and over, because you're not going to have enough time to take the rest of the test if you do that. Okay, we're expecting that you're going to be using the calculator, and on the calculator this would be the probability that X is greater than or equal to 30 is 1 minus the probability that X is less than or equal to 29. Right, there was a number of you that put 30 in here. Right, which is kind of a minor mistake. This says at least 30, which means greater than or equal to, not strictly greater than 30. Okay, so that was a kind of a minor mistake. Now, you should know that on the calculator, you can put in binomial CDF. This gives me the probability that X is less than or equal to 29. And if you only wrote this stuff down without labeling these up here, you're going to get at most a partial. Okay? Now, the idea here is that this is not standard statistical notation. This is the notation that Texas Instruments uses. All right, so when we come up with our answer, you need to identify what do these numbers represent. Okay, this number is the sample size, and this is the probability of a success. Okay, you really don't need to label this thing as anything because you've kind of taken care of it up here. Okay, and then give me the answer. Right, a third way that you could do this, and this is not something I saw a lot of you do, is to use a normal approximation. All right, so the distribution of X is approximately normal. Okay, and actually using this notation here, you could say X follows a normal distribution with a mean that's equal to 22.3 and a standard deviation that's equal to 4.16. Okay. Now, if you did this and you did normal CDF, you would need to tell me what's the lower bound, what's the upper bound, what's the mean, what's the standard deviation if you wrote out normal CDF here. Okay. In addition to that, you've also got to justify that you can use a normal approximation, and that's by saying that NP and NQ are both bigger than or equal to 10. All right, so this was actually a little bit more work if you did this with a normal approximation. All right, so what I've done here is I've gotten all the points several different ways. Okay, I would say go with whatever your teacher told you was the easiest way to do this. If it's binomial, and if you use this notation, that's great. If not, you need to write it out in words, or if you're using the calculator, make sure that you label these things. Okay, otherwise you're not going to get credit for the work. Okay. And I guess that one only had the two parts. Okay, then for question number, oh no, this one had a third part. Okay, part C. Suppose that a stratified random sample design is used to select 30 women and that meet the age requirement and 70 that don't. Okay, so if we look at the probability of not meeting the age requirement, if we did a stratified sample, we're going to get exactly 30 out of 100 that don't meet the requirement. If we did a simple random sample, this is our answer from part A. Okay, so a lot of you said it's more likely with the stratified sample. Okay, but again, you've got to be very deliberate with your answer. Okay, a woman is more likely not to meet the age requirement in the stratified random sample. Okay, that's the right answer. But then you really do need to say because 30% is bigger than 22.3%. Okay, there are some things like this that I don't particularly like, but I understand why they're there. Okay, this test is really a test of your communication skills as well as your math skills. All right, and so communicating, what do these numbers tell me about my answer? Well, I need to know that you're saying this number is bigger than this number, so this is more likely to happen in a stratified sample. Okay, so again, assume that the reader can't read your mind. Okay, make sure that you tell them everything you know. Okay, then question number 4 was about activity trackers. And they took a random sample of people, 61 people in New York City, who wear activity trackers. And they selected those people, and the number of steps taken on a typical workday for each person in the sample was recorded. Okay, the mean was 9,797, and the standard deviation was 2,313. Okay, a couple of things that many of you skipped over is telling me what kind of an interval it is that you're doing. Okay, and one way to do that is just to name it like that. A second way to do it is to name it using the formula. Okay, and I think it's good practice for you to write the formula out like this. This is the sample mean plus or minus. Many of you used a z-star here. Okay, but this is a sample standard deviation, not the standard deviation of the entire population. Okay, so if you use the formula like this, that also tells me what kind of an interval you're doing. So either this or this is what we want to see. Practically, I think that most of you probably just put it in the calculator, and this is the interval. Okay, so you've got to give me the interval, and then you've got to show me, what is it you did there to get the interval. All right, and then also, whenever you see construct, you almost will always see this followed by interpret. Right? And some of you just gave me the interval and forgot to interpret it. Okay, we're looking for really 4 things in the interpretation. A confidence level. So tell me I am whatever confident level you are, that the mean number of steps, okay, and it's important that you're talking about a mean in this case, not a proportion or not a number of steps, but the mean number of steps taken on a typical workday for all people working in New York City who wear a tracker is between the lower bound and the upper bound. Okay, so we're looking for a confidence level. We're looking to see, are you talking about a population parameter or are you talking about the sample statistic? Okay, we need to be talking about a population parameter, and then we also need context. Okay, and the context here is people working in New York City who would wear a tracker. Okay, so 4 different things we're looking for in the interpretation. So the interpretation is almost as important, if not more important, than the actual interval. Okay, so common mistakes, we see this all the time. Some people forget to check the conditions. Okay, it's important that this is a simple random sample. Okay, and it didn't say simple random sample. A lot of times in these problems they'll just say a random sample. Okay, you can assume that that is simple random sample. And then you also need to justify that we can use a normal approximation because the sample size is big enough. Okay, we have a big enough sample that we can build the confidence interval from the formula. All right, that one I think just had the one part to it. Okay, then the next question. It looks like this one is going to get into some linear regression, but it never really does. This is running times. This is how long it takes you to run the race, and this is how long it takes you to react to the starting gun. Okay, and then this one says we want to circle the point on the graph that represents the runner who won the race. All right, so we want somebody who has a short running time and also a quick response time or a reaction time. All right, and I circled these three down here because when I first did this problem, I looked at all three of those points. I knew that the winner had to be down here in the bottom left-hand corner somewhere. Okay, but then if you think about how do you calculate the time it took them to run the race, we need to add together their reaction time and the running time. All right, and this one, if you approximate this as 0.152 and 9.61, right, and we're a little bit lenient on the approximations there. I want to see those two things added together and give me an approximation. All right, and because we're rounding off these two numbers, okay, any number that was between 9.75 and 9.765 were acceptable. Okay, all right, but again, we really want to see what numbers did you add together to get the total time. Okay, so show the left-hand side of the equation as well as the answer. Okay, and then the follow-up on this one was, based on the graph, is it reasonable to assume that reaction time and running time are independent? All right, so if they were independent, then it really wouldn't matter how fast you could run the race. The reaction time didn't depend on that. All right, and if you go back to the graph, you can see that the people that are down here in this bottom corner are fast runners and quick reactors. The ones that are up here are generally slow runners and slow reactors. All right, so because there is this positive association between running time and reaction time, I would say that they are not independent. Okay, and you could say this a couple ways. I said it appears as if the faster runners tend to have faster reaction times. Okay, and I probably should have included that slower runners have slower reaction times. Okay, therefore, there's a positive association and they are not independent. So make sure you answer the question as well. All right, and then part C has to do with extrapolation. It says, suppose you've got a person who has a reaction time of 0.3 seconds. Okay, would you use this model to predict how fast they could run the race? Okay, now 0.3 is pretty far outside the range of values that we have data for, right? And so if we extrapolate and we go up here and say that value should be somewhere up here, right? That's not necessarily something that we can do because, first of all, this is outside the range of observed reaction times. And in addition to that, what happens outside of that range might change for larger values for the reaction time. In other words, this distribution might go like this for a while, and then maybe about here it starts to, level off. Okay? The thing is, we don't know what it does outside of this range. Therefore, it's extrapolation is not appropriate. Okay, so that was question 5, right? And then I want to get into question number 6. And I'll tell you that question number 6 sometimes will freak students out because, well, first of all, it's an important question. It does end up being the equivalent of 1/8 of your final exam score. So getting a 4 on this is really nice to get your grade up, okay? But the other thing that kind of freaks people out is there's typically something in this question that your teacher has never talked about in class. right? And that's the nature of this question is what can you do with um, if you're posed with a situation that you're not familiar with, okay? How can you build on the stuff that you already know in order to answer the question? Now, the other thing is that there will be an investigative task part of this question, but there's also going to be some parts of this question that should be easy, okay? And so concentrate on the easy parts. And in addition to that, look at what they're asking you and why would they ask me these questions in this particular order. A lot of times what they're trying to do by the way the test is constructed is to lead you in the right direction. Okay, now with this question number 6, I'm expecting that an average student could probably get 2 out of the 4 points on this pretty easily. Okay, part A on this one is a condition for obtaining an interval estimate for a population proportion is approximately normal. Is it reasonable in this case? All right, so really what we're doing here is we're just saying n times p and n times q, are these bigger than 10? Okay, and so we really want to see the work here. Okay, this is n, and then this number you could either give me as a decimal or you could give it to me as a fraction. Okay, when I multiply them together, I'm going to get 44, and same thing here, I'm going to get 356. All right, and then I also need to say this, that they're both bigger than 10, so that justifies that the sampling distribution is approximately normal. Okay, and then for part B, the standard error of p hat. Okay, well, this is a formula that you actually have on your formula sheet. And so we take the sample proportion of successes and the sample proportion of failures and divide by the sample size. And you're going to get 0.0156. Okay, so again, the work and the answer are both very important. Okay, we will see a lot of students will try to calculate something like this on their calculator. They'll write this down correctly and then they'll screw it up. Okay, they'll forget to close the parenthesis at the end of the square root or something like that, right? And so they'll have this side correct and have the wrong answer here. They're going to get full credit. Okay, you would get full credit just for writing that, actually. Okay, so then we move on. So that's stuff that's not new. Okay, and then for part B, let's see, that was part B. Part C, okay, part C, how many standard errors is the observed p hat from point 1? So the observed p hat was 11%. Okay, 44 out of 400. All right, minus 10% and then divide by the number that I got in part B. And I end up with, I thought that my decimal was off here a little bit, but it was 0.641. Okay, so 0.11 is 0.641 standard errors away from 10%. Okay, so far, again, this is pretty straightforward. All right, and then we get to part D, where they're saying that they're going to take two proportions and they're going to average them. Right? So we've got this formula. Okay, probably this is not something that you've done in class. All right, but what we want to do is part D, number 1, or part 1, is pretty straightforward. All we're going to do is take our answers that we calculated earlier and plug them in. Okay, this is typical of a very simple kind of a question that is asked on the AP exam. Plug those two numbers in and evaluate it, and we're going to get 0.185. Okay, and then to find the standard error, okay, the standard deviation of the sampling distribution, we need to remember that when we combine, this is basically you're taking px and py, adding them together, and then multiplying by 1/2. All right, so we saw that if two observations are independent, then their variances will add, and then multiply that by a constant. That constant is going to get squared. All right, so we take the variance of px, the variance of py, we add those together and we multiply by 1/2 squared. Okay, a lot of you forgot to put this in here. Okay, and so what's in pencil is the variance. The variance is equal to 1/2 squared times the sum of the variances. Then to get the standard deviation, take the square root of that, which is the square root of that, which is that number. Okay, so this is a little bit different, but it is something that you should have seen somewhere in the course. All right, and then we get a little bit further, and this is where the investigative task comes in. So consider these hypotheses. The average proportion of light bulbs that are defective is 10% versus the alternative that the percent of defectives is more than 10%. So a reasonable statistic is this. Okay, and again, part E, they're just asking you to evaluate it. So we take our previous answers and plug them in. All right, now you might ask, well, what if we didn't get the right answers on the previous parts? That's fine. Okay, as long as you show me the work and you plugged in your answer to, I think this was part B and part C, okay, you are going to get full credit for that, even though this number will be wrong. Okay. Something else that might happen is you might not have any idea how to find this number, and you might not have any idea how to find this number. And in my experience with grading the exams during the summer, there are some pretty clever students that will say, I mean, just explicitly, they'll write, put a circle here, and they'll point an arrow to it and say, I don't know how to get the previous answer to part whatever, but if I did, I would put that number here. I don't know how to get the previous part of the answer, but I would put that answer here. Okay, and then they give me a number. Okay, or they might say, I don't know how to find these two numbers, but if I did, I would put them here. So let's pretend that this number is, and just plug a number in, and this number is, and plug a number in. Okay, don't skip this one because you don't know what these two numbers are. Okay, go back and say, boy, we must have calculated those someplace. Oh, if I could have done part C, I would have gotten the answer for here, and if I could have done part D, I would have got the answer for here. That's perfectly fine. That's you know, it sounds like that's not very good statistics, but you know what? That's pretty good test-taking strategy. Okay, and so we end up with this is 6.343, and that is a number of standard errors away from the mean. Okay, then we run into this thing, Chebyshev's inequality. All right, this is something that I don't see in very many current textbooks. Okay, it's not something that you should be thinking, oh, I got to go back and I got to learn about Chebyshev's inequality. You don't have to do that, okay? Because they're going to give you enough information to tell you what it says. And it's saying that this inequality states that the proportion of any distribution that lies within k standard errors of the mean is at least this number. Okay, well, this is the number of standard errors away from the mean, so we need to see that you take that number and plug it in for k. Right? And when you do that, you're going to get about 97.5%. So we're saying that 97.5% of all test statistics are going to lie within 6.343 standard deviations of the mean, or standard errors of the mean. Okay? So the probability of obtaining a test statistic that is as large as 6.343, and I should have said or larger, is about 2.5%. Okay, this 2.5% is going to act like a p-value. So since the p-value is less than 5%, we have sufficient evidence to suggest that d is bigger than 10%. Okay? So honestly, this question number 6, other than this part here, it should have been pretty easy for you guys to work through that. Okay, and I'm saying pretty easy. There are some things that you need to know, but it's all manageable. Okay, go back and look at the order of the questions. A lot of times you're going to be taking parts of one question and using them in another part of the question. Okay? All right, so So that's the exam. And I'm hoping that by going through this exam with you all, that you get an idea of the places where you could pick up some of the easy points. Okay, that's the whole purpose of doing a mock exam, is to learn from the mistakes that you made. All right, and I don't know that a lot of students understand what is expected of them to write down on the exam. Okay, I think that if you had written down everything that I wrote down in pencil on my paper, you're going to end up getting every point. Okay, you don't have to get every point in order to get a good grade. Okay, if you get 2s on most of these questions, you're doing pretty well. Okay, if you can get 2s or 3s on all 6 of the questions, you're probably going to score a 4 or a 5 on the exam. Okay, for your total cumulative grade. Okay, if you can get 3s and 4s consistently on these questions, you're going to get a 5. Okay, so don't think that you have to get all the points in order to get a good grade on the exam. Okay, so I want to wish all of you good luck. I hope that this has been a learning experience, and I hope that it's been a valuable experience, and that you guys will perform well on the AP exam. And again, I hope to be able to work with your teachers again next year. And one more time, good luck on the AP exam. And that's all I got to say. All right. Thank you again for the opportunity to meet with you and to put together this video. I appreciate your time. Thanks. Bye.